Have you ever stopped to think about what lies beneath your feet or hidden within the walls of the buildings all around you? It's a vast, hidden network, a circulatory system for our modern world. And at the heart of it all is something incredibly simple, yet fantastically strong: the humble steel pipe. We rely on them for almost everything. They bring clean water to our taps for a morning cup of tea and carry away the wastewater afterwards. They transport the natural gas that heats our homes and cooks our food. They even form the very skeletons of skyscrapers, bridges, and stadiums, providing the strength that allows us to build bigger and higher than ever before. It's an incredible amount of responsibility for one object. These metal tubes are the unsung heroes of our daily lives, working tirelessly out of sight. Imagine a world without them. Cities couldn't exist as we know them. Industries would grind to a halt. The complex web of services we take for granted, from plumbing to energy to construction, would simply fall apart. So, while you might not give a second thought to a steel pipe, its presence is fundamental to our comfort, our safety, and our progress. It's a testament to human ingenuity that we can take raw elements from the earth and transform them into such a vital and robust tool. The story of how they're made is a fascinating journey of immense heat, colossal pressure, and pinpoint precision. Today, we're going inside one of the giants of industry, a modern steel pipe factory. We're going to pull back the curtain on this incredible process from the very beginning to the very end. We will follow the journey from a pile of raw, earthy materials to a perfectly formed, incredibly tough steel pipe ready to be shipped out and put to work. It's a process that combines raw, brute force with the delicate touch of advanced technology. You'll see gigantic machines that roar and hiss, capable of molding solid steel as if it were clay, working alongside sophisticated computers that measure and check every single millimeter. It's a symphony of engineering, a dance of fire and metal. So, get ready to witness a truly amazing transformation. We'll explore the science behind creating one of the world's strongest materials and marvel at the engineering that shapes it. We will see how a factory, buzzing with activity and powered by cutting-edge technology, turns basic ingredients into the arteries that keep our world flowing. This is more than just manufacturing. It's about building the very backbone of our civilization, one incredibly strong, perfectly round pipe at a time. The scale of the operation is something you have to see to believe, a place where human skill and machine power come together to create something truly essential. Let's get started. Every great creation starts with a recipe, and making steel is no different. You can't just dig it out of the ground. It has to be made, carefully, and precisely. The main ingredient, the star of the show, is iron. This comes from iron ore, a reddish-brown rock mined from the earth. But iron on its own isn't strong enough for the tough jobs we need steel pipes for. It's a bit too soft, a bit too brittle. To give it the legendary strength we associate with steel, it needs a partner. That crucial partner is carbon. It might seem strange that adding a bit of a soft black powder can make a metal so much tougher, but that's the magic of chemistry. The carbon usually comes from coal, which is baked in special ovens to become a purer form called coke. It's this coke that gets added to the mix. But the recipe doesn't stop there. Just like a chef adds spices to a dish to get the perfect flavor, steel makers add other elements to create different types of steel with specific properties. These are called alloys. For example, chromium and nickel are often added to make stainless steel, which is famous for its ability to resist rust and corrosion. Manganese is added to increase hardness and strength, while silicon helps to remove impurities. Every single ingredient is carefully measured out, because even a tiny change in the recipe can dramatically alter the final product. Another hugely important ingredient in our modern steelmaking recipe is scrap steel. Think of it as recycling on a massive scale. Old cars, washing machines, demolished buildings, and even leftover bits from the factory itself are collected and sorted. Using recycled steel is fantastic for two reasons. Firstly, it's brilliant for the environment. It reduces the need for mining new iron ore and coal, saving energy and natural resources. Secondly, it's incredibly efficient. It takes far less energy to melt down existing steel than it does to create new steel from raw materials. This makes the whole process cheaper and more sustainable, a win-win for both the factory and the planet. Once all these materials arrive at the factory, the iron ore, the coke, the alloying elements, and the mountains of scrap steel, they are stored in massive yards. Huge cranes and powerful conveyor belts move everything into place, ready for the next stage. It's a logistical ballet of giant proportions. The raw materials are carefully organized and prepared, because the quality of the final pipe depends entirely on the quality of the ingredients that go into the pot. Getting this first step right is absolutely critical. The slightest mistake here could compromise the strength and integrity of the pipes that will one day carry precious resources or support massive structures. Now we get to the really hot part. With all our ingredients gathered, it's time to cook. The heart of this stage is the furnace, and in a modern steel mill, this is often an electric arc furnace, or EAF. This isn't your oven at home, it's a colossal, cauldron-like vessel capable of withstanding unbelievable temperatures. The process begins as giant cranes lift and drop the carefully measured mix of scrap steel and other raw materials into the EAF. It's a noisy, dramatic start, with tons of metal crashing down into the belly of the beast. Once the furnace is loaded, a heavy lid swings into place, sealing it shut. The real show is about to begin. This is where the electric part of the electric arc furnace comes in. 3 enormous graphite rods called electrodes are lowered down through the lid until they are just above the metal. Then, a massive jolt of electricity is sent through them, enough to power a small town. This creates a spectacular, intensely hot arc of electricity that leaps from the electrodes to the metal. The temperature inside the furnace skyrockets to over 1,650 degrees Celsius. That's hotter than volcanic lava. The intense energy from the electric arc begins to melt the solid steel, turning it into a glowing liquid sea of orange-white metal. It's a violent, roaring process, but one that is controlled with incredible precision. While the steel is melting, the recipe is fine-tuned. Samples of the molten metal are taken and analyzed by a computer in a nearby lab. This tells the steelmakers the exact chemical composition of the mix. If it needs a little more of something like manganese for strength or silicon to remove oxygen, these alloys are now added to the fiery brew. A powerful jet of oxygen might also be blown into the furnace. This helps to burn off any remaining impurities like excess carbon which bubble out of the liquid steel. It's like a high-tech version of a chef tasting the soup and adding a final pinch of salt to get it just right. After about an hour or so of this intense heating and refining, the steel is ready. The furnace is tilted by powerful hydraulic rams, and the brilliant liquid steel pours out into a massive container called a ladle. This process is known as tapping. As the molten steel cascades out, it looks like a river of pure sunlight, a truly mesmerizing sight. The ladle, which is lined with special heat-resistant bricks, will now act as a transport vessel, carrying the super-hot liquid to the next stage of its journey. The first major transformation is complete. We have turned a pile of cold, solid metal into a perfectly crafted liquid steel, ready to be shaped. The journey of our molten steel is far from over. It's currently in the ladle, a giant bucket holding tons of fiery liquid. But a bucket of liquid steel isn't very useful. We need to turn it back into a solid, but in a very specific shape that's easy to work with. This is where a brilliant piece of engineering called the continuous caster comes in. This machine performs a seemingly magical trick. It takes a continuous flow of liquid steel and turns it into a long, solid strand of steel without ever stopping. It's a non-stop production line that is far more efficient than the old method of pouring steel into individual molds. The ladle is lifted by a huge overhead crane and positioned high above the continuous casting machine. A valve at the bottom of the ladle is opened, and the molten steel begins to pour out in a controlled stream. It flows into a special water-cooled copper mold at the top of the caster. This mold is the shape we want our steel to be in, either a square, which is called a billet, or a circle, known as a round. As the liquid steel touches the cold walls of the mold, a thin solid skin immediately begins to form, like ice forming on a lake. This skin is crucial, as it holds the still liquid core inside. The partially solidified strand of steel is now slowly and continuously drawn out from the bottom of the mold. It looks like a long, glowing red snake of metal. As it emerges, it is sprayed with jets of cool water. This process, called secondary cooling, helps the rest of the steel to solidify gradually from the outside in. This controlled cooling is incredibly important. If it cools too quickly, the steel can become brittle and crack. If it cools too slowly, the internal structure might not be right. The speed of the strand and the amount of water are carefully controlled by computers to ensure the steel solidifies with the perfect properties for making strong pipes. As the long strand of steel moves further down the line, it continues to cool and becomes completely solid. Finally, at the end of the casting machine, powerful torches or giant shears automatically cut the moving strand into manageable lengths. These freshly cut pieces, still glowing a dull red and radiating intense heat, are now called billets or rounds. They are the raw, solid blocks of high-quality steel that will be sent to the pipe mill for the next stage of their transformation. We have successfully turned a chaotic liquid into uniform, solid building blocks, ready to be shaped into their final form. The factory's pulse is steady and strong, producing the fundamental material for the pipes. Before we can make a pipe, our newly formed steel billet needs to be prepared for the intense shaping process ahead. Although it has solidified, it's not yet at the perfect temperature for being pierced and stretched. The billets, which have cooled to a dark red or even black, are moved from the continuous caster to the next major area of the factory, the reheat furnace. This is another giant, incredibly hot chamber, but its job isn't to melt the steel, but to heat it back up to a precise, uniform temperature. The billets are loaded onto a moving hearth that carries them slowly through the long furnace like loaves of bread moving through a giant oven. Inside this reheat furnace, powerful gas burners heat the billets to a specific temperature, usually around 1,200 degrees Celsius. At this temperature, the steel doesn't melt, but it becomes soft and malleable, with a consistency a bit like plasticine. It glows a bright, brilliant orange-yellow, indicating it's reached the perfect state for shaping. This reheating process is critical. If the steel is too cold, it will be too hard to shape and could break the powerful machinery. If it's too hot, it could lose its structural integrity. Sensors and computers monitor the temperature constantly to ensure every single billet is heated perfectly all the way through to its core. Once a billet reaches the other end of the furnace, it is ejected, glowing brightly and ready for action. It immediately moves onto a set of rollers that transport it to the first stage of shaping. This is often a machine called a rotary piercer, but before it gets there, it might pass through a descaler. As the billet was heated, a thin layer of iron oxide or scale formed on its surface. This scale is hard and brittle and must be removed. The descaler blasts the billet with jets of high-pressure water, which instantly knock off the dark scale, revealing the pure, glowing orange steel underneath. It's like giving the billet a quick, powerful shower before the main event. Now the real fun begins. The clean, super-hot billet is ready to be transformed from a solid block into a hollow tube. It is pushed towards the rotary piercer, a formidable machine that will perform an act of pure mechanical might. This initial preparation, the careful reheating and cleaning, is all about setting the stage for success. Every step is calculated to ensure the steel is in the optimal condition for the immense forces it is about to endure. The factory floor hums with anticipation as the perfectly prepared billet, a glowing projectile of pure potential, hurtles towards the machine that will give it its hollow heart. This is the moment of creation, where a solid block of steel becomes a pipe. The process is called seamless pipe manufacturing because the final product has no seam or weld line, making it incredibly strong. The star of this show is the rotary piercer. Imagine two massive, barrel-shaped rolls, spinning in the same direction and angled slightly towards each other. The glowing hot billet is pushed between them. As the rolls grip the billet, their angle forces it to rotate rapidly while also pulling it forward. This intense spinning and squeezing action does something amazing. It causes the very center of the solid billet to break apart, creating a small cavity. Just as this cavity starts to form, a hardened, pointed tool called a piercer point or mandrel is pushed into the center of the billet from behind. The billet is literally forced over this point. It's an act of incredible brute force, as the machine simultaneously squeezes the outside of the billet with the rolls, while pushing a hole through its core with the mandrel. The result, emerging from the other side of the machine, is a thick-walled, rough-looking tube called a hollow shell. It's happened in a matter of seconds. We've taken a solid block of steel and punched a hole right through its length, creating the basic form of a pipe. But this hollow shell is far from finished. Its walls are often uneven in thickness and its diameter isn't precise, so it immediately travels down the production line to another machine, often called a plug mill or a stretch-reducing mill. Here, the still hot shell is passed through a series of smaller and smaller rollers. A new mandrel is held inside the pipe to control the internal diameter, while the rollers on the outside squeeze the pipe, reducing its wall thickness and its outer diameter. This process effectively stretches the pipe, making it much longer and thinner, just like rolling out dough with a rolling pin. Each set of rollers it passes through makes the pipe longer, thinner, and more uniform. This is all happening at incredible speed, with the long, glowing pipe snaking its way through the mill. Computers control the speed and pressure of every single roller to ensure the final dimensions are exactly what the customer ordered. By the end of this process, our short, thick, hollow shell has been transformed into a much longer pipe with the correct wall thickness and diameter. It's still glowing hot and needs a few more finishing touches, but the fundamental shape is now locked in. It's a testament to engineering, turning raw power into precise form. Our pipe has been pierced and rolled, but the journey isn't quite over. As it cools, the long steel tube can develop slight bends or curves. A crooked pipe isn't much use to anyone, so the next crucial step is to make it perfectly straight. To do this, the pipe is sent through a straightening machine. This machine uses a series of specially angled rollers that apply pressure to the pipe from multiple directions. As the pipe rotates and passes through these rollers, any bends or warps are carefully ironed out. It's a bit like rolling a pencil between your palms to make it straight, but on a much bigger and more powerful scale. After straightening, the pipe, which has now cooled to a much duller red or even black, needs to be cut to the exact lengths required by the customer. A giant, fast-moving circular saw, or an abrasive cutter slices through the long pipe, creating individual pipes of a precise, uniform length. The ends of these newly cut pipes are often rough or uneven from the saw, so they are sent to a machine that bevels or faces the ends. This machine shaves a small amount of metal off each end, creating a clean, smooth surface and often cutting a slight angle or bevel, which makes welding the pipes together on a job site much easier. Now that the pipe is straight, cut to length, and has clean ends, it might undergo some final heat treatments. Depending on the customer's requirements for strength and durability, some pipes are reheated in another furnace and then cooled in a very controlled way. This process, known as quenching and tempering, can change the microscopic crystal structure of the steel, making it even tougher or more flexible. It's like a final baking process that locks in the desired mechanical properties, tailoring the pipe for specific high-pressure or high-stress applications, such as in a deep-sea oil pipeline or a power plant. Finally, the finished pipes may be given a protective coating. To prevent rust during transport and storage, they are often coated with a thin layer of oil or a special varnish. For pipes that will be used in corrosive environments, a more robust coating might be applied, such as a layer of zinc in a process called galvanizing, or even a thick plastic or epoxy coating. The pipe is now physically complete. It has been transformed from a solid block into a straight, perfectly sized and finished tube, ready for the most important stage of all, proving it is strong and safe enough for the job. Making a strong pipe is one thing, proving it is another. Before any pipe is allowed to leave the factory, it must pass a series of rigorous tests. This is quality control, and it is arguably the most important stage in the entire process. The safety of people and the environment depends on these pipes performing flawlessly, so there is absolutely no room for error. The first check is often visual and dimensional. Inspectors carefully examine each pipe for any surface imperfections, and highly precise laser gauges measure the pipe's diameter, wall thickness, and straightness to ensure they are within the tiny, acceptable tolerances. Next comes the test of strength. A small piece is cut from a sample pipe and taken to the mechanical testing lab. Here, a machine called a tensile tester grips the piece of pipe and pulls it apart with immense force. Computers measure exactly how much force it takes to stretch the steel and eventually break it. This confirms that the steel has the required strength and ductility, the ability to stretch without snapping. Another test, called a Charpy impact test, involves striking a notch sample with a heavy pendulum to see how it behaves in cold conditions, ensuring the pipe won't become brittle and fail in low temperatures. One of the most critical tests for a seamless pipe is the non-destructive examination. We need to check for any hidden flaws inside the steel without cutting the pipe open. To do this, factories use advanced technology like ultrasonic testing. The pipe passes through a machine that sends high-frequency sound waves through the steel wall. If there is any internal crack or imperfection, the sound waves will bounce back differently, and a computer will flag the exact location of the flaw. This is similar to how a medical ultrasound lets a doctor see inside a human body. It's a high-tech way to ensure the pipe's internal structure is perfectly solid. Finally, many pipes must undergo a hydrostatic test. The pipe is filled with water, sealed at both ends, and then the water pressure is increased to a level far higher than the pipe will ever experience in normal service. The pipe must hold this immense pressure for a set amount of time without leaking or bursting. This is the ultimate proof that the pipe is leak-proof and strong enough to handle its intended job safely. Only after a pipe has passed every single one of these checks, dimensional, mechanical, non-destructive, and hydrostatic, is it finally given a stamp of approval and deemed ready for shipment. After passing the gauntlet of quality control, our steel pipes are officially ready to begin their working lives. The approved pipes are stenciled with important information: the manufacturer's name, the pipe's size and grade of steel, and a unique heat number that traces it all the way back to the specific batch of molten steel it came from. This provides complete traceability, which is crucial for safety and quality assurance. The pipes are then carefully bundled together with strong steel straps, making them easier and safer to handle, transport, and store. It is the final act of preparation within the factory walls. The bundled pipes are then moved by cranes or heavy-duty forklifts to the factory's storage yard or directly to the shipping area. From here, their journey to the outside world begins. Depending on their final destination, they might be loaded onto the back of large trucks for domestic delivery, or placed onto railway cars for transport across the country. For international customers, the pipes are transported to a port where they are carefully loaded into the holds of massive cargo ships, ready for a voyage across the oceans. Each step of this logistical chain is planned to protect the pipes from damage, so they arrive at their destination in perfect condition. And what a variety of destinations they have. Some of these pipes might be heading to a construction site to become the structural columns in a new hospital or airport terminal. Others might be destined for a new housing development, where they will form the underground network for water and gas. A batch could be on its way to a remote oil or gas field, where they will be welded together to create a pipeline stretching for hundreds of miles across harsh terrain. Yet another bundle might be going to a manufacturing plant to be used as rollers or components in other industrial machinery. The applications are almost limitless. The next time you turn on a tap, see a skyscraper reaching for the clouds, or drive over a long-span bridge, take a moment to think about the incredible journey of the steel pipes hidden within. From a carefully measured recipe of raw materials, through the fire of the furnace and the immense power of the rolling mill, to the rigorous scrutiny of the testing labs, each pipe is a product of immense power and incredible precision. These unseen arteries, born in the heart of the factory, are out in the world, quietly and reliably doing their job, forming the strong, essential framework that supports our modern way of life.